Hello everyone, my name is MEETKUMAR Mahendrabhai Patel, student ID is 225115045. Welcome to my SIT 706 Cloud Computing Final Project presentation. In this presentation, I will walk you through two phases. In phase 1, I deployed a highly available WordPress application on AWS. In phase 2, I designed a cloud-native serverless architecture for an e-commerce platform that addresses 8 specific business requirements. All work was completed using AWS Learner Labs in the US East 1 region, which is North Virginia. Let me start with a high-level overview of what was accomplished in each phase. So in phase 1, the WordPress deployment, I created a custom VPS spanning two availability zones with 4 subnets, 2 public and 2 private. I launched EC2 instances running WordPress connected to a MySQL RDS database. I set up an application load balancer to distribute traffic and auto-scaling group to handle scaling between 1 and 3 instances. S3 for media storage, and finally, I automated the entire infrastructure using AWS Cloud Formation templates. In phase 2, I designed a completely different architecture, a serverless e-commerce solution. This uses ECS Fargate and Lambda instance instead of EC2, DynamoDB instead of a relational database. Elastic as Redis for session management, CloudFront for global current content delivery, and Aurora Global Database for disaster recovery. The design meets a recovery point objective of 15 minutes and recovery time objects of 1 hour. Let me now walk through each component in detail. This is the architecture diagram for phase 1. As you can see, we have a VPC with CIDR block 192.168.0.0/16. At the top, we have the internet gateway allowing public internet access. Traffic from users hits the application load balancer, which sits in the two public subnet across availability zone A and B. The ALB distributes traffic to EC2 web servers running in the private subnets. These servers cannot be accessed directly from the internet. They only receive traffic through the ALB. This is the key security design decision. At the bottom, we have the MySQL RDS database, also in private subnets, with multi-availability zone enabled for automatic failover and a read replica for read scalability. The net gateway in public subnet 1 allows the private instances to reach the internet for updates without being directly exposed. Let me explain the networking setup in more detail. I created a custom VPC with a /16 CIDR block, giving us over 65,000 IP addresses. This was divided into 424 subnets, each with 256 addresses. Public subnet 1 and public subnet 2 are in availability zones, US East, US East 1A and US East 1B, respectively. These subnets host the application load balancer and the net gateway. They have auto-assign public IP enabled and route internet traffic through the internet gateway. Private subnet 1 and private subnet 2 are also across both availability zones. These host our web servers and RDS database. They route outbound traffic through the net gateway, meaning instances here can download updates but cannot be reached from the internet. I created separate route tables. The public route table directs 0.0.0/0 to the internet gateway, and the private route table directs to 0.0.0/0 to the net gateway. This separation is essential for the security model. RDS MySQL. For the database layer, I deployed Amazon RDS running MySQL version 8.0.40. The original requirement was version 8.0.35, but this was unavailable in the US East 1 region, so I used 8.0.40 instead. The RDS instance is a db.t3.micro deployed in a custom DB subnet group containing only the two private subnets. Public access is disabled. The database is completely isolated from the internet. One important configuration is the security group. The RDS security group only allows inbound traffic on port 3306 and only from the web server security group. This means only our web servers can talk to the database, nothing else. After the initial deployment, I enabled multi-availability zone. This creates a synchronous standby replica in a different availability zone. If the primary database fails, AWS automatically promotes the standby, typically within 60 to 120 seconds. This gives us 99.95% uptime SLA. I also created a read replica in a separate availability zone. Unlike the multi-availability zone standby, a read replica can serve read traffic, reducing the load on the primary database. In a production WordPress site with heavy read traffic, this can significantly improve performance. For the compute layer, I launched an EC2 instance running Amazon Linux 2023. The original requirement was Amazon Linux 2, but this was unavailable in the Learner Labs environment. This required adapting the user data bootstrap script instead of using yum and Amazon Linux extras, which are Amazon Linux 2 commands. I used DNF, the package manager for Amazon Linux 2023. The script installs Apache PHP and the required PHP extension, then downloads and configures WordPress. Once WordPress was installed and configured to connect to the RDS endpoint, I accessed it via the EC2 public IP address and completed the WordPress setup wizard, providing the database name, username, password, and the RDS endpoint. After confirming everything worked, I created an Amazon machine image or AMI from this configured instance. This AMI captures the entire state of the server, including WordPress, Apache, and all configurations. This AMI is then used in the launch template so that any new instance launched by the autoscaling group is an exact copy of this working server. For the IAM instance profile, I use the lab instance profile provided by AWS Academy, which includes permission for S3 access and system manager, session manager. For media storage, I created an S3 bucket named WordPress Media S22511504. Public access is blocked at the bucket level. I applied a bucket policy that restricts access exclusively to the lab role IAM role. This means only EC2 instances with the lab instance profile can read from or write to this bucket. This follows the principle of least privileges. In WordPress, I installed the offload media plugin by EchoWebs. This plugin redirects all media uploads from the local EC2 file system to the S3 bucket. After configuration, when I upload an image in WordPress, the file URL points to S3 rather than the local server. This is a critical design pattern for auto-scaled applications. If media was stored locally on EC2, it would be lost when the auto-scaling group terminates an instance. By storing media in S3, our EC2 instances become truly stateless. They can be safely terminated and replaced without any data loss. The application load balancer is the entry point for all user traffic. It is internet facing and deployed across both public subnets, giving its high availability across two availability zones. The ELB security groups allows inbound HTTP traffic on port 80 from anywhere, since this is the public facing component. I created a target group called WordPress DG with health checks configured on the WordPress login.php path. This means the ELB regularly checks if each backend server can serve the WordPress login page. If a server fails the health check, the ELB stops sending traffic to it. Using an ELB instead of directly accessing EC2 instance provides several benefits. It distributes load evenly, performs health checks, and provides a single stable endpoint that doesn't change when backend instances are replaced. The auto-scaling group is configured with a minimum of one instance, a maximum of 3, and a desired capacity of 1. Instances are launched into the private subnet using the launch template I created earlier with the WordPress AMI. I configured two dynamic scaling policies using simple scaling. The scale out policy creates a CloudWatch alarm that monitors average CPU utilization. When it exceeds 70% of one evaluation period of 5 minutes, the ASG adds one instance with a 300-second cooldown period. The scaling policy works in reverse. When CPU drops below 25%, the ASG removes one instance again with a 300-second cooldown. The cooldown period is important. It prevents the ASG from launching or terminating instance too rapidly, which could cause instability. I tested the ASG by manually terminating the running web server. With a few minutes, the ASG detected the missing instance through the LB health check and automatically launched a replacement in a private subnet. This demonstrates the self-healing capability of the architecture. Security is a critical aspect of this architecture, and I implemented it using a chain-based security group model following the principle of least privilege. The ELP security group is the outmost layer. It allows inbound HTTP on port 80 from anywhere, the entire internet. This makes sense because the load balancer is the public entry point. The web server security group is the second layer. It only allows inbound HTTP on port 80 from the ELP security group. This means our web server can only receive traffic from the load balancer, not from the internet directly, not from any other source. The RDS security group is the innermost layer. It only allows inbound MySQL traffic on port 3306 from the web server security group. The database can only be reached by our web servers. This creates a strict traffic flow, internet to ALB, to web server to RDS. No component is unnecessarily exposed. If an attacker compromises the load balancer, they still cannot directly access the database because the RDS security group blocks everything except traffic from the web server security group. During implementation, I encountered several challenges that required adaptation. First, Amazon Linux 2 was not available in the Learner Labs environment. I adapted by using Amazon Linux 2023 with the DNF package manager instead of yum. Second, IAM create role permission. So it was not was restricted. Instead of creating a custom EC2 WordPress role, I used the pre-provisioned lab instance profile. Third, MySQL engine version 8.0.35 was unavailable. So I used version 8.0.40 instead. These challenges actually reflect real-world cloud deployment scenarios. Cloud environments constantly change, AMIs are deprecated, engine versions are updated, and permission model vary across accounts. The ability to adapt and find alternative is a key skill for cloud engineers. So cloud formation infrastructure as code. So to demonstrate infrastructure as code, I created two cloud formation templates. The first template, the network stack, provision all networking resources, the VPC for subnets, internet gateway, net gateway, and route tables. It exports key resource IDs using cloud formation outputs so the second stack can reference them. The second template, the application stack, provisions the security groups, RDS instance with multi-availability zone, application load balancer, target group, launch template, auto scaling group, and CloudWatch scaling alarms. It imports the VPC and subnet values from the network stack using cross-stack references. I split this into two stacks because networking and application infrastructure have different life cycles. The network rarely changes, while the application stack might be updated frequently. Both stacks deployed successfully with create complete status. This proves the entire infrastructure can be produced with a single set of template files, enabling consistent, repeatable deployment across environment. So I perform comprehensive testing to verify all components work correctly. First, WordPress was accessible via the ALB DNS name, confirming the load balancer, target group, and backend servers all are functioning. Second, I terminated the running web server and observe and the auto scaling group automatically launch a replacement instance within a minute. Third, I connected to EC2 instance via AWS Session Manager, no SSH keys or Bastion host needed. Fourth, I uploaded a photo in WordPress and confirmed the file was stored in S3 with the URL pointing to the S3 endpoint. Fifth, the RDS console confirmed multi-availability zone deployment was active. And sixth, both cloud formation stacks have create complete status. Yeah, the challenges and adaptation is already covered. So I'll go to phase two, business requirements. Now let me move to phase two, where I was given a business scenario for an e-commerce company migrating to AWS. The company has eight key requirements. They accept exponential growth doubling annually. They need the lowest possible latency with persistent shopping cart sessions. They want a serverless and event-driven approach with a managed service to reduce. They want to replace their slow, expensive relational database. All data must be encrypted and transit at rest. They need improved global response time for international users. And finally, the design must meet a recovery point objective of 15 minutes and a recovery time objects of 1 hour. Let me show you the architecture I designed to address every one of these requirements. This is my proposed architecture. Let me walk through each layer. At the top, global user connect through Amazon CloudFront, a CDN with over 400 edge locations, which catches static content close to users worldwide. AWS WAF protects against web attacks, and Global Accelerator route dynamic traffic through the AWS backbone for lower latency. Route 53 handles DNS with health check based failover route routing. If the primary region fails, traffic automatically redirects to the secondary region. The application layer uses ECS Fargate for containerized workloads, no EC2 management needed, and AWS Lambda for event-driven processing like order confirmation and inventory updates. API Gateway provides a managed API layer. Elastic Cache Redis stores shopping cart and session data with sub-multi-seconds latency. Even if a user disconnects and reconnects, that session persists. For the database, DynamoDB replaces the relational database for simple table structure like product catalog and cart. It scales automatically with on-demand capacity. Aurora Serverless V2 handles complex transactional data like orders and payments. On the right side, the secondary region in US West 2 has Aurora Global Database Replica and DynamoDB Global Tables, providing RPO under 1 second and automatic failover within minutes. Let me explain why I choose this specific service over alternatives. So I choose ECS Fargate over EC2 because Fargate eliminates server management entirely, no patching, no capacity planning, in auto scales based on demand, and you only pay per task. I choose DynamoDB over RDS for the product catalog because the company said their table structure is simple. DynamoDB's key value model fits perfectly, and on-demand capacity handles the expected exponential growth without over provisioning. I choose Elastic Cache Redis over DynamoDB for session because rapid Redis provides sub-milliseconds latency for the frequent small reads and writes typical of session management. I choose CloudFront over a simple S3 static website because CloudFront supports both static and dynamic content, integrates with the WF for security, and has 400 plus edge locations. Aurora Global Database was chosen for disaster recovery because it provides a continuous application with under 1 second RPO, well within the 15-minute requirement. So to summarize, this project demonstrated end-to-end cloud architecture skills. Phase 1 delivered a production-grade, highly available WordPress deployment with auto-scaling, load balancing, and infrastructure as code. Phase 2 addressed all 8 business requirements through purpose-built AWS managed services, serverless compute, NoSQL database, global CDN, and multi-region disaster recovery. The key takeaway is that cloud architecture is about choosing the right service for each workload, not defaulting to familiar tools. Thank you for watching. Thank you very much.